Hi guys, I am Divyang from IGCSE on Fingertips. Today we are going to cover AS Chemistry, the whole syllabus. Let's quickly get started. So the first topic is atomic structure. In this topic, we understand that there are protons, neutrons and electrons in an atom. Everything is made up of an atom. Protons and neutrons are at the center of the atom, which is known as nucleus, and this nucleus has a nucleon number, that is the total number of protons and neutrons. They are not equal. Always the number of protons and electrons are equal. Atom is naturally stable, right? Sorry, stable, I mean atom is naturally neutral. Sometimes even if atom has same number of protons, two atoms, if you look at them, if you have same number of protons, let's look at carbon, right, 12 and 13, it can have different number of neutrons. So 6 protons, 6 neutron here, 6 protons and 7 neutrons here, 14 carbons, 6 protons and 8 neutrons. Even then the chemical properties of all the three atoms will be same, because their outermost shell electrons are also same, and the chemical properties depend on outermost shell electrons and not the neutrons. Then how are these electrons arranged in an atom? To understand that, we already know this, right, that there are 2 electrons in the first shell, 8 in the second, 18 in the third, and so on and so forth, something like 2n square. We know this rule, but this has been modified a little. It was found out that this is not the exact arrangement. Okay, so there is first shell which contains subshell. A subshell can contain orbitals. Okay, so it was found out that if it is the first shell, it can contain only one subshell, which is S. If it is the second shell, it can contain two subshells, which is S and P. If it is the third shell, it can contain three subshells, S, P and D. If it's the fourth shell, it can contain three subshells. Now, the capacity to accommodate electrons for each subshell is different. S subshell can accommodate 2 electrons at max. P subshell can accommodate 6 electrons at max. D subshell can accommodate 10 electrons at max. F can accommodate 14 electrons. Now, if it does not matter if it is 2s subshell or 3s subshell. If it is s subshell, it can accommodate only 2 electrons. Now, let's look at uh, aluminium, right? Aluminium has an atomic number of 13, and now let's try to accommodate electrons. So generally what we would do, we will say it is 2, 8 and 3, but with the new configuration, it is in the first shell there is one subshell which contains 2 electrons. In the second shell there is first subshell which contains 2 electrons. The second subshell can have 6 electrons, so 10 electrons are accommodated. Third subshell accommodates 2 electrons, so now I have 12. And then, so third shell, first subshell contains 2 electrons, and then the leftover electron goes here. Now, how to draw the orbitals, right? I said shells has subshells, subshells has orbitals. S has one orbital. In each orbital, any subshell can contain only 2 electrons, right? There are tricky questions that so and so shell, how many electrons can its orbital contain? One orbital, no matter of what subshell, can contain only 2 electrons. But so this is 1s, but what will happen when you go to 2p? Let's see. So 2s also has 2 electrons, but if you go to 2p, right, it has 3 subshells. Sorry, 2p is itself a subshell. It has 3 orbitals. The first orbital gets 1 electron. The second one will keep it like this. Why? I'll tell you in some time. And the third one goes here. So 3, 4, 5 and 6. These are the arrangement of electrons. In 3s again like this, and 3p just 1 electron, which will be like this, right? 2 plus 2 4, 4 plus 6 10, 10 plus 2 12, 12 plus 1 13, and 13 electrons of aluminium. Now why did I accommodate all the electrons in this way? This is a direction, right? It says that they are going in this direction, and when I make a half arrow like this, it means that half of the electrons are going in this direction. What will this achieve? This will decrease the repulsion between electrons that are in the same orbital, right? Electrons are negatively charged. Now naturally, what does electron and atom do? They try to decrease this repulsion so that more electrons can be accommodated equal to the number of protons, so that the atom can be neutral. Now to achieve that, to decrease the repulsion, the electrons are in opposite spin. They are spinning in opposite direction, right? So this is that. Now just I will tell you that with copper and chromium something different happens. Chromium has an atomic number of 25, I think, and copper has 29, right? Here copper has 3d and 4s subshells as the outermost subshells. It will have 10 electrons here and 1 here. Chromium 3d has 5 here and 4s2 here. Now what is so special about this? To understand this, right, let's keep this as the center. Let's understand how do we accommodate, how do I decide the order that 3p has to be filled only after 3s. How do I find that? For that we will give number. Already the shells have number, right? 1 2 3 4 5 6 7. I'll give s as number 0, p as 1, and d as 2, right? So I want to decide, let's say, that who gets filled first, 3d or 4s, right? That is what we are talking about here. So 3 as number 3 itself, and what is number given to d? It is 2, so 3 plus 2, and 4 is the number itself, and s has been given number 0, so plus 0. This total is 4 and this total is 5. So 4s gets filled first. This is what is happening. Okay, this is what is happening. 4s gets filled first, and only then 3d will get filled. And how will the orbitals look like? So 1 2 3 4 and 5, right? So the orbitals will look like something. So these are the 5 electrons. They are trying to accommodate as much space as possible to decrease the repulsion. Okay, now once I know this, that the lower number gets filled first, there might be another confusion. If you look at 3p, right, 3 plus 1 is also 4. So out of 3p and 4s, who gets filled first? The one with the lower principal number, the one with the lower shell number gets filled first. So 3p will be filled, then 4s will be filled, and then 3d will be filled. Now what happens here is that 4s in case of copper has just 1 electron and 3d has 10 electrons. So even when 3d was filled after 4s, 4s remained incomplete and 3d got complete set of electrons. Why does this happen? Because 3d, if it has 9 electrons, it is unstable. An incompletely filled subshell or shell or orbital is less stable. Half filled is somewhat better stable, and fully filled is most stable, right? Fully filled is the configuration of noble gases, right? Outermost shell filled or outermost subshell filled, that is the configuration of noble gases. So what happens is a little bit of compromise in energy, that 4s, if it has 2 electron, this will have 9 electrons, right? This is unstable. Half filled is better stable or more stable. So 4s gets less stability, but not so much as incompletely filled, and this is the compromise that takes place. Now the next topic we have is ionization energy, right? First let's understand what is ionization energy. The energy required to remove an electron from an atom is known as ionization energy. The energy required to make it a positive ion. So how will I ionize sodium? I will form Na plus by removing one electron, right? Now ionization energy depends on a lot of things. It depends on nuclear charge, distance from the nucleus, shielding, and spin pair repulsion. Let's see all of them one by one. So if I talk about nuclear charge, let's compare sodium, magnesium and aluminium, right? The number of electrons and protons in sodium is 11, in magnesium is 12, in aluminium it's 13, right? Now the nuclear charge on magnesium is higher than sodium, on aluminium it's higher than magnesium. So what will happen? The electrons are attracting protons more, the protons are attracting electrons more. Let's see what will that lead to. Distance from the nucleus, right? So if I go from group in group 1 from period 1 to period 5, let's say, right? So the distance from the nucleus will increase, right, as the number of shells are increasing. What will that do to ionization energy? We'll see. The shielding. What is shielding? So if you look at the sodium atom, right, it has 11 protons here and then there are electrons around it. Okay, there are 2 electrons here, 8 electrons here, and finally 1 electron here, right? 4 and 4, 8, right? There is 1 electron there. Now what will happen is that these electrons are being attracted by these protons, but these outer electrons are being repelled by the inside 2 electrons, and the outermost electron is being repelled by the other electrons. So in a way we can say that electrons are shielding the outer shell electrons from the attraction of protons, right? That is known as shielding. And spin pair repulsion, as I've already showed you in case of orbitals, that these 2 electrons are already repelling each other. If the spin pair repulsion is more, it is easier to remove an electron from the outermost shell. So let's look at now what happens. If nuclear charge increases, the ionization energy, the energy required to remove this electron, will increase. If the distance from nucleus increases, the energy required to remove this electron from the outermost shell decreases. So sodium will have a higher ionization energy compared to potassium, right? Then shielding. If shielding increases, the energy required to remove the electron, ionization energy decreases. And if spin pair repulsions increase, then the energy required to remove that electron decreases, ionization energy. Right? Now, what is atomic radius and what is ionic radius? This is a part of periodicity, but let's understand it right now only. So atomic radius, what is happening here? We've already discussed that the nuclear charge is increasing when you go from left to right in a period, right? So the atomic radius, the distance between the nucleus and the outermost shell electron, because shielding is same, right? All of them have equal inner electrons, but they have higher charges, the higher nuclear uh, protons and electrons. So their atomic radius goes on decreasing. But if you look at their ionic radius, right? If I remove 1 electron from sodium, if I remove 2 electron from magnesium and 3 electron from aluminium, all of them are ions, right? All of them have equal number of electrons in their outermost shell. But now what will happen? Here 11 protons attract 10 electrons. Here 12 protons attract 10 electrons, and here 13 protons attract 10 electrons, right? So aluminium will have highest attraction. It will keep on attracting electron more towards itself. So when you go from left to right in a period, the ionic radius decreases, right? But when you go from top to bottom in a group, the ionic radius will increase because the number of shell increases by 1 when you go to the next period in same group, right? Then the next topic we have is stoichiometry. What is stoichiometry? Stoichiometry is nothing but mole concept, right? So what is AR? AR is relative atomic mass, right? Mass of an atom compared to the carbon 12 atom, where the mass of carbon 12 itself is 12 gram, right? So if I compare hydrogen with carbon 12 atom, hydrogen has a mass of 1 gram if the mass of carbon 12 atom is 12 gram, so on and so forth, right? Then number of moles is found out by the formula that measured mass upon relative mass. So it can be a molecular mass, it can be formula mass, or it can be just atomic mass. So for example, if I want to find out what is the molar mass, what is the mass of 1 mole of carbon dioxide, I can say that it has 1 carbon, so 12, plus it has 2 oxygen, so 16 into 2, 32 plus 12 is 44. So 44 gram is relative molecular mass of carbon dioxide, but it is also molar mass of carbon dioxide. So if I have 22 gram of carbon dioxide, number of moles is 22 upon 44, which is equal to 0.5 mole. Okay, 1 mole of a gas is equal to 24 dm cube. 1 mole of anything has 0.6.022 into 10 to the power 23 particles, which is also known as Avogadro's number, right? Moles is not conserved. So in an equation where C plus O2 gives CO2, 1 mole of carbon combined with 1 mole of oxygen to produce just 1 mole of carbon dioxide. So 1 plus 1 is not equal to 2. In fact, they are not added, they are combining, right? Then mole ratio is maintained. 1 mole of carbon will always produce 1 mole of carbon dioxide. So no matter how many moles of oxygen greater than carbon there are, if I take 0.5 mole of carbon, I will have 0.5 mole of carbon dioxide. That ratio is always maintained, right? Now, as I've already talked about isotopes, right? We try to find out the relative abundance of isotopes. So let's say, for example, chlorine has two isotopes, 35 and 37. Now in 1 mole of naturally occurring chlorine or 1 mole of extracted chlorine, how many of the atoms will be 35 and how many of them will be 37? How will we find that? We will use mass spectrometer. Now we don't need to understand how does it do it, but it can tell us that okay, 75% of your atoms were 35 mass and 25% of your atoms were 37 mass. What I will do to find out the relative mass now, I'll say 25. This is known as abundance, by the way, right? So 25 upon 100 into 37 plus 35 into 75 upon 100. Whatever this answer is, that will become my relative atomic mass of chlorine, because the abundance of isotope says that, right? So what does this number actually mean? It also means that if I take 1 mole of chlorine, it will not weigh 37, it will not weigh 35, it will be somewhere in between, right? We know that it is 35.5, but maybe with this calculation you will not get 35.5. These are not actual percentages, okay? And last but not the least here, that concentration is equal to mole upon volume, mole of solute upon volume of the solvent. We assume that the solute does not increase the volume of solvent, it gets dissolved in the solvent, okay? Now we also see empirical formula in the same chapter. We'll do questions from that because this chapter has been rigorously done in your IGCSEs in your grade 10. So I will not go a lot into this topic, and we will see balancing of ionic or redox reactions. Let's take one example. Okay, let's say MnO4 minus, right? It reacts with Fe. Just a second. MnO4 is oxidizing agent. Oxidizing agent meaning it oxidizes something else. So it itself gets reduced, it gains electrons, so makes Fe2 2 plus to Fe3 plus, right? Now they have asked me that if this produces Mn2 plus at the end, right, what is the balancing of this reaction? Now always remember that if it's a redox reaction, there is an unlimited supply of H plus, there is an unlimited supply of electron, and there is an unlimited supply of H2O, right? We will not consider electrons right now, but H plus and H2, I can add it on whatever side I want. Ideally, we will add water on the right hand side, we will add H plus on the left hand side. Why and when? Let's see. First, let's check. I made an equation. Is it correct or not? MnO4 is an oxidizing agent. Oxidation is loss of electrons. So it will make the other thing lose electrons. Yes, iron is losing one electron. So the first step is to find what is the change in oxidation state. Iron goes from 2 to 3. So the change in oxidation state is 1, right? Let's compute the oxidation state of manganese here. So let's say it is X and 4 times of -2, because oxygen has an oxidation state of -2. This whole becomes -1 charge, right? So I have found that X minus 8 is equal to -1, or X is equal to +7. So oxidation state of manganese here is +7, and here it's clearly stated that it is +2, right? So here the change in oxidation state is 5. First step, right? And let's take another pen. So first step is multiply the oxidation state. This is getting reduced by 5 numbers. So I'll multiply 5 here. Okay, I'll multiply 5 here. This is changing by 1, so I'll multiply 1 to the other one. So the number of oxidation state change in the one that is getting reduced is multiplied to the one that is getting oxidized, and the oxidation state change in the one that is getting oxidized is multiplied to the one that is getting reduced. Hopefully this is not that confusing, right? So I'll just erase this, and then comes the next part of the balancing. Now this is 5Fe, this is 5Fe, so this is balanced actually, right? But if you look at the number of charges, that is still imbalanced. So there is 10 positive charge, 10 minus 1, right? So there is 9 positive charge on the left hand side. This is 15, 15 plus 2, 17. So 17 positive charge on the right hand side. As I said, we can add H as many as we want. What is the difference? The difference is of 8. So I'll add 8H plus here. What is remaining to balance? Oxygen and hydrogen is remaining to balance. I have 4 oxygen, 8 hydrogen. I can easily add 4H2O on this side, and this reaction is balanced. So iron, the oxidation state change in iron multiplied to manganese, oxidation state change in manganese multiplied to iron, then balance the charges, balance the hydrogen, and that is your answer. This is how you balance redox reaction. Hopefully that is clear. Then there is chemical bonding. There are 4 types of chemical bonds. What are they? Ionic, covalent, metallic, and coordinate. Ionic meaning exchange of electron, covalent meaning sharing of electron, coordinate meaning again sharing, but only one of them is offering electron to the other, right? We will see how it happens in ammonia, right? Sorry. So we have nitrogen. Nitrogen has 1 lone pair of electron and 3 hydrogen bonded with it already. If there is an H plus meaning it does not have any electron. Nitrogen can offer its electron to H plus, saying that okay, you can keep these electron but cannot take them away. I will also keep this electron. So what will happen? This will form a complex NH4 plus. This is an example of coordinate bonding, right? Metallic bonding, bonding between metals, between the cations of metals and the delocalized electrons. Now each of them have different properties due to their bonding, right? Bonding and property of materials. So metallic will be good conductors of electricity, good conductors of heat, because the attraction is very strong between the cations and the electrons. They will have high melting point and high boiling point. But what will happen with ionic? They'll have high melting point, high boiling point, because oppositely charged ions are getting attracted towards each other, which is forming a giant bond, right? Which is forming a giant structure. So their melting point is high, boiling point is high, but they cannot conduct electricity when solid. But when you mix them in water, due to polarity of water, which we'll see what is now, but due to polarity of water, they will get dissolved in water and can conduct electricity. The ions can become charge carriers. In covalent bond, the attraction between two molecules is weaker. So generally covalent compounds have lower melting and boiling point. They are generally gases or liquids, and they do not conduct electricity in any situation, right? The other one is coordinate. So they are generally in solutions. They, if it is, let's say, MgSO4, right? In that SO4 is formed due to some kind of coordinate bonding, but in that case it's a salt and it is also a part of ionic compound, right? But SO4 itself will appear only in a solution, so we don't need to see a lot of properties of that in that chapter. No, that is in the states of matter. Going ahead, we have VSEPR, valence shell electron pair repulsion theory. This will dictate shape of an atom, sorry, shape of a molecule. You need to go in your textbook and you need to look at every combination they have shown. They will not ask anything outside those combinations, so you need to learn them. The only logic you need to remember is the strongest repulsion is between a lone pair and a lone pair, weaker repulsion between lone pair and bond pair, and the weakest repulsion is between a bonded pair and bonded pair. So for an example, if I look at NH3, right, this is a bonded pair and bonded pair, and then there is a lone pair here, right? Two electrons making a pair. There are two electrons which nitrogen has. So this repels these two bonded pairs stronger compared to these bonded pair repelling each other, right? So this is a type of triangle happening. So hydrogen are here, sort of a tripod, right? And then a lone pair of electron here. If hydrogen comes here, okay, this will still be in the same shape. Coordinate bond does not change repulsion. Okay, it will still be the same, and the angle between all of them will be 109.5. You're expected to remember the angles, but you don't have to compute any angles. You just look at your textbook, remember all of them. Okay. Then we have intermolecular forces, which will give rise to what I was talking about, polarity, right? Now, have you imagined that water is liquid, right? But H2S is a gas. Comparatively, H2S should be a liquid as well, right? Because sulfur is just below oxygen, but it is not. Why? Because of something known as electronegativity. What is electronegativity? Electronegativity is the property of an atom to pull the shared pair of electron towards itself. So in the bond of hydrogen and oxygen, they are sharing one electron each, right? What should have happened is these electrons should be here somewhere at the center of this bond. But because oxygen is electronegative, what it will do? It will take away these electrons away from hydrogen and a little bit towards itself. When this happens, it gets a slight negative charge. This gets a slight positive charge, right? Because there is difference in electronegativity, charges are made. Although they are not complete charges, they are slight charges, right? They are partial charges, but these partial charges, they are permanent for a molecule like water. Okay, the actual shape of water is like this, right? Because two lone pair on oxygen, right? So this is what happens. Sorry. Okay, this is what happens. So minus delta. Okay, what will happen here is, let's have a broader look. Okay, let's keep it here. Let's have a broader look to this. What will happen here? So this is an oxygen molecule. This is already negative delta, positive delta, positive delta. So this will be attracted to a negative delta and positive delta, positive delta. This will have another negative delta and there will be positive delta, positive delta. So the hydrogen and oxygen, right, they will be attracted to each other in water. This attraction will lead to stronger intermolecular forces, which is why water is liquid. So these are known as permanent dipole, right? This oppositely charged molecule is known as dipole. They are permanently there in case of water, they are permanently there in case of HCl, they will be there in case of HF, they will be there in case of any hydrogen bonded to nitrogen or oxygen. So in NH also there is a dipole existing, right? Because of which this permanent dipole, if there is hydrogen, the attraction is very very strong, because hydrogen is very weak to attract those electrons towards itself. This gives rise to something known as hydrogen bond. It is the strongest type of intermolecular force. Hydrogen bond is due to polarity, polarity is due to electronegativity, and this is all permanent dipole, right? So what else is possible? Something like this is possible, that one bromine, I always forget this, sorry. So one bromine molecule and other bromine molecule may approach each other in this manner, right? So when this bromine is randomly moving here, because there is very huge concentration of electrons here and obviously very huge concentration of electrons here, but because this is moving towards the center of this, the shared pair of electrons will move a little bit towards the bromine at the bottom. So this will form a positive and a slight negative charge. This is very very temporary, right? It is not permanent. But because this becomes positive delta, the bromine near it will become, sorry, because this becomes negative, this becomes positive, and some other bromine which is attached to this bromine by covalent bond becomes negatively charged. This will again give rise to one more dipole, one more dipole. So this is an instantaneous dipole induced dipole force. So ID forces, these are temporary, but they also are a type of intermolecular force. So bromine will attract another bromine, but not as strong as water attracting another molecule of water. So although ID are weaker forces, they do exist. So two types of intermolecular forces, mainly ID and PD. Instantaneous dipole induced dipole and permanent dipole forces, right? Then we have already understood the bonding and property of materials. So we can move to the next slide, and we have states of matter. There are three states of matter: solid, liquid and gas, right? In gas, there is something known as ideal gas. An ideal gas is a gas which obeys the gas law equation, or inversely, if it obeys a gas law equation, it is known as an ideal gas. What is an ideal gas? So gases are supposed to or assumed to have very low intermolecular forces. So if I talk about two molecules of oxygen, they do have very weak intermolecular forces. That is why they are gas. Otherwise they would be liquids or solid. Like iodine, they have stronger intermolecular forces, and that is why iodine is a solid. Now because they have very low intermolecular forces, the two molecules of gas, they interact with each other very very less, right? So in 1 meter cube of volume of a room, there can be only, like, I can fill the whole volume of this room with 100 molecules of gas, right? It's not like they'll try to come close to each other, right? If I compress them to 1 centimeter cube, right, I can still have just 100 molecules and they'll still not interact with each other. And the molecule itself is so small, right? Let's say if one molecule is equal to a ball, okay, of a cricket ground, then the space around it, which is empty, is larger than a cricket ground. So what do we say here? We say that the volume occupied by the molecule itself is negligible compared to the volume of the molecule. Sorry, I said it the wrong way. The volume of the molecule is negligible compared to the space it occupies, the empty space around it. So we assume in a mathematical way that the volume of a gas molecule is negligible. Now see, this is not correct. What is a matter? Matter is something that has mass and occupies space. Now if I say gas does not occupy space, is it correct? Is it matter anymore? No, it's not. So we get into problems when there are extreme conditions. What are these extreme conditions? When temperature is very low, the particles are moving with very low uh, velocity. When they are moving with very low velocity, we expected them to not interact with each other at all. They start interacting with each other, right? And if the pressure is also high, when the temperature is really low, if the pressure is also high, they start coming together, and we would expect them to have some volume, but the actual volume they occupy is lesser than what we expect theoretically, because they are now getting attracted to each other. But even then, if you keep on pressurizing them, we've already assumed that gas molecules do not occupy space. But if you go on compressing them endlessly, what will happen? They'll not get compressed after a point, which means that the space they occupy or their own volume is not actually negligible, right? So in extreme conditions, gases do not remain ideal, but in experimental conditions, they remain ideal, and we can use this equation PV equals to nRT, where P is pressure in Pascal, V is volume in meter cube, N is the number of moles of that particular gas, R is constant 8.314, T is temperature in Kelvin. You can use this equation to plot a lot of things. Let's say it is given to me that temperature remains constant. If pressure is increased, what will happen? In that case, I find that PV equals to a constant. So if pressure increases, volume has to decrease to keep that constant a constant, right? So I can use this equation to answer a lot of questions like that. Then there is vapor pressure. So what is vapor pressure? Vapor pressure is the pressure exerted by vapor phase on its liquid phase. As simple as that. It was asked a couple of times, so I thought I should explain this to you. Then there are a lot of solid states. There is fullerene, and then there is graphene and all of that. Look at the textbook, read it once. They are asked very rarely, but they are in syllabus and important nevertheless, right? Then we have enthalpy changes, right? So the question is enthalpy changes. See, enthalpy is the total energy change in a reaction. Okay. So if we want to find is the reaction endothermic or exothermic, we try to find out the enthalpy changes. If enthalpy change is negative, we say that the reaction is exothermic. If enthalpy change is positive, we say that the reaction is endothermic. We've already understood this with the help of bond energy in your IGCSE, right? What we had done is, let's say if it is CH4 plus O2 gives CO2 plus H2O, what I'll do? I'll find out the bond energy of carbon hydrogen, find out the bond energy of oxygen, find out all the energy, right? Delta H is equal to energy of products minus energy of reactants. So if the energy of products is greater than the energy of reactants, then it will be positive, but if it is lesser, then the reaction will be negative, which means that basically on this energy diagram, if this happens, this much energy is given out, which is the enthalpy change. This was the activation energy. Here it is exothermic. If this happens, right, then this is endothermic change, right? But now we have something known as Hess law or Hess cycle, which is a logical extension of conservation of energy, which helps us to find this. We'll look at examples of this, right? We will also see how H is equal to mc delta theta is used to find this, but we also sometimes use bond energy like we used to do in our IGCSEs to find out the answer to this. Then we have equilibrium. What is an equilibrium? Equilibrium is when a reversible reaction reaches a point where the rate of forward reaction is equal to the rate of reverse reaction and the concentration of the reactants and product remains constant, right? There is no visible change. It's a dynamic equilibrium. There are changes taking place. We cannot measure them anymore, right? Now, we've already learned that what happens with reversible reactions. So the favorite reaction N2 plus 3H2 gives 2NH3, right? In this reaction, we know that this is an exothermic reaction, right? It was explained to us once and again that if you increase the temperature, what will happen? If you increase the pressure, what will happen? Iron should be a catalyst, this and that and all of that, right? Now we cannot judge everything by looking at all the facts, right? I must have some quantifying thing some quantifying thing where I can find out how to judge all of this. So for that you have something known as Kc and Kp. What is Kc? Coefficient of concentration, right? It is given by the concentration of products upon concentration of reactants. Let's find out. NH2 plus 3H2 gives 2NH3, right? So what will be the Kc for this reaction? What is the product? NH3 raised to power 2. Why? It is influenced by a stoichiometric factor of 2 upon N2, right? And H2 raised to power 3. Why 3? Because changing the concentration of H2 has a power of 3, right? It can influence it thrice. So that is what it is. So this is the value of Kc. Now every time for every reaction I might need to find out the units of Kc. Here the this box means concentration. So concentration square is mole per dm cube whole square upon mole per dm cube. 3 plus 1 4, so I'll write raised to power 4, square goes and 2, so I have dm raised to power 6 and mole raised to power minus 2. This will be the unit for Kc for this particular reaction. It might change for other reaction. You'll have to find it every time, and sometimes just finding the unit gives you some mark. Then Kp, if this is about concentration, you can guess Kp is going to be about partial pressure. I'll explain what partial pressure is, but partial pressure of NH3 square upon partial pressure of N2 multiplied by partial pressure of H2 raised to power 3. Okay, that is the equation for Kp. Again, just like Kc, Kp will have individual units for each reaction. If you look at this, we will measure pressure in Pascal. So we have Pascal square and we have Pascal raised to power 4. So the final unit is Pascal raised to power minus 1, right? P capital. Okay, please. Thank you. Pascal raised to power minus 2. Now, here it might look like they are same, but the Kp coefficient can only be used for gases. So if there were some reactants which were not gas for this equation, let's take some equation like that. Let's say we have A plus B gives C, but out of this only B is a gas and C is a gas. So my Kp will be equal to partial pressure of C upon partial pressure of B. Now if the stoichiometric ratio is 1:1, this Kp is actually unitless, right? Because unit gets cancelled out. Now the Kp will depend only on the partial pressure of the gases. right? Because solids, they cannot be compressed, so pressure cannot change anything, right? Now once we know that how can they act, let's understand first that what can change the coefficient of concentration and what cannot change the coefficient of concentration. It stays constant if concentration changes. So what will happen if I increase the concentration of NH3 in this reaction, right? If I increase the concentration of NH3, what will happen? The concentration of H2 and N2 will increase. The reaction will, the equilibrium will shift towards left. The concentration will increase in such a way that Kc remains constant. If I increase the pressure, right, it again does the same. The equilibrium shifts to the side where pressure is lesser and it tries to keep the value of Kc constant. But if temperature changes, because this reaction is exothermic, right? If temperature changes, then the concentration changes, which cannot be in a fixed ratio, right? Because the rate of forward reaction increases, or if I increase the temperature, for this particular case, the rate of backward reaction increases more than the increase in forward reaction, right? And therefore the equilibrium itself changes. When the equilibrium changes, Kc does not remain constant anymore. But if there is a change in temperature or pressure, in case of Kp, what will happen? Kp itself will change, right? If I increase the pressure, position of equilibrium changes, Kp changes. To which side? It will change to the side where number of moles are less, right? And if I increase the temperature, it will shift to the side where the reaction is endothermic. We will see that in the example. Now we should be doing what is partial pressure, and we should be trying to understand how does it work. So basically, let's say I have N2, 3H2 and 2NH3 in my equilibrium. Okay, let's say equilibrium is already established and I have 1 dm cube of vessel in which the reaction is taking place. Volume occupied by N2 is equal to 1 dm cube. Volume occupied by H2 is 1 dm cube. Volume occupied by NH3 is also 1 dm cube. But the pressure exerted by N2 is proportional to the mass of M2, right? Pressure exerted by H2 is proportional to the mass of H2. Pressure exerted by NH3 is also proportional to the mass of NH3. The higher the mass, the more the pressure it exerts, right? So it's like each gases, because they have individual masses, they will exert individual pressure. But because gases have a lot of space in between them, they don't come in between, and we can say each gas is occupying all the space that the mixture is given, right? Now, based on this, what do we have? We have that something known as partial pressure. Partial pressure is the partial pressure exerted by this particular gas. It will be equal to its mole fraction. So, the partial pressure exerted by N2 will be equal to the moles of N2 upon the moles of N2 plus moles of H2 plus the moles of NH3 in the mixture, right? This is what basically it is. And then we have the equilibrium of how an acid base reaction takes place, right? So we need to, they may ask you to decide what indicator to use, or they may ask you to draw this graph. Okay, so keep it very very simple. If it says that base is being added to acid, right, then the graph would be something like this. All of these graphs are when acid is being added to a base, right? If the acid is strong, right, acid and base. So if acid is strong, base is also strong, the graph will look something like this. What is a strong acid? An acid that can give a lot of H plus ions, or the one that can ionize completely, right? So organic acids are going to be weak acids, mineral acids are going to be strong acids. Bases, same thing, they can accept H plus ions, they are strong, they can accept less H plus ions, they are weaker, or ionize less, they are weaker. So a strong acid and strong base, the graph will look something like this. Now, here what you have to take care of, you have to remember at what volume do you show the maximum slope. Okay, so let's say it is sodium hydroxide and HCl, right? This will give me NaCl and H2O. So if the concentrations are equal, and generally they are in these type of questions, the volume of sodium hydroxide and volume of HCl will be equal. So if they tell me that I am adding acid to 20 centimeter cube of 1 mole per dm cube of sodium hydroxide, then the maximum slope should be at 20 centimeter cube of HCl. But instead of HCl, let's say if this was H2SO4, which gives Na2SO4 plus H2O, right? So I must add a 2 here. So if 20 centimeter cube of 1 mole per dm cube of sodium hydroxide was there, and I was adding H2SO4, then the neutralization point will be 40 centimeter cube. Just be vigilant of this thing, that you have to always check with the equation that how much of the other solution needs to be added for neutralization to take place, right? This diagram is trying to show us that in this change, phenolphthalein will not be a correct indicator, because it changes color between 10 and 8.2 pH. But here the sharpest curve is at around 7 pH. So I need to use bromothiamine. There is a table in your textbook. You can find all the values here. This is when the volume of strong acid, right? The acid is strong. This flat line shows you that acid is strong and the base is weak. Okay. Also, the pH reveals that the base is weak. This happens when base is strong and acid is weak. Okay. And we also had one more, when both the acid and base, both of them are weak. So the graph was something like this. It will be in the range of something 9 and 4, right? It will end before 4, taper off before 4, and start at somewhere around 9. Again, the steepest will be around 7 only, right? The graph is important, shape of the graph is important, and the volume at which you show maximum slope is important. Okay, coming back to this, rate of reaction, the next topic. What is rate of reaction? The rate at which product appears, or the rate at which reactant disappears, right? I can measure it in the form of mass per unit time, volume per unit time, or concentration per unit time. But more on numericals in next year in your A levels. Right now, what do you have is, how does rate of reaction change? If I increase the temperature, the particles with enough energy to react increases, more frequent collision takes place, because when temperature increases, the velocity of the particle also increases. So more frequent collision, more particles with enough energy to react. So the rate of reaction increases, no matter which side of reversible reaction it is. If temperature increases, the rate of reaction must increase. If pressure increases, same thing happens, the rate of reaction must increase. Okay. Then if concentration increases, the rate of reaction increases. If surface area increases, rate of reaction increases. All of this has the same reason, that number of successful collision increases, and therefore the rate of reaction increases, right? So what is a successful collision? Let's say H2 reacts with Cl2 to produce HCl, right? In this, hydrogen may collide with another hydrogen. Hydrogen may collide with another chlorine molecule. It may also collide with another HCl molecule once the reaction has started. but only hydrogen colliding with chlorine will react if both of them have enough energy to react. This reaction is known as successful reaction. Okay. Now, why and how does the energy increase, or to observe the increase in energy is shown by Boltzmann distribution of energy. So this is the number of particles with this much energy, and this is the energy. So very high amount of energy is with very less number of particles. Most of the particles have a intermediate level of energy. Okay, and activation energy is somewhere around here. So only these particles can right now react. But what happens when I increase the temperature? So let's say this is the Stephen Boltzmann graph for temperature T. When I increase the temperature, this graph is, let's say, 10 plus T or T plus 10. Now what happens? The slope shifts a little bit towards right and goes down because now the distribution gets better. Some particles here have very high energy, some have very low energy. So what will happen when I increase the temperature? Particles with lower energy will get less. Now more particles have more energy, right? So if this was activation energy, previously only these many particles had energy to react. Now all of these particles have enough energy to react, which will change the rate of reaction, increase the rate of reaction. What does a catalyst do? A catalyst decreases the activation energy. So now these many particles have enough energy to react, and therefore it increases the rate of reaction. It does so by introducing an alternative pathway, does not get used up by the end of the reaction, which is why it is catalyst, right? So that is what a catalyst does. Then we have periodicity, where we talk about behavior of elements in their period, or what can we predict from the placement of an element in the periodic table. Atomic radius, if you go from left to right in a period, what will happen? The atomic radius will decrease. We have discussed this already. What will happen to ionic radius? It will decrease. What will happen to atomic radius when you go down the group? It increases because one shell increases. What will happen to ionic radius? It will increase because again one shell is increasing. Conductivity, we start with metals and we end to non-metals and then noble gases. So conductivity goes on decreasing. Melting point, again metallic bonds, giant bonds, we slowly move to molecular bonds, and then finally also we have molecular bonds, and the halogens are diatomic molecule, and then we have finally noble gases that are monoatomic. So melting point also decreases. First, ionization energy, the energy required to remove an electron, this first ionization energy will go on increasing. Why? Because the nuclear charge goes on increasing and it becomes more and more and more difficult to remove that electron. But this graph, it's particularly interesting because we see a lot of bumps here. See what's happening. First ionization energy of magnesium is greater than sodium. Yes, because nuclear charge is greater. But aluminium's first ionization energy is lower than that of magnesium. Why? Because if you remember, the outermost shell of magnesium is 3s2, but the same for aluminium is 3p1. 3p1 is a little bit further away compared to 3s, and therefore if it is little bit further away, it becomes easier to remove that electron, and therefore the first ionization energy of aluminium is less than that of magnesium. Then silicon. So this increase is logical. Why does this happen again? Same thing. Now what happens? Aluminium has the outermost shell in outermost electron in 3p1, and silicon has 3p2, right? After silicon we have phosphorus, it has 3p3. So what is the configuration? This is the shell, this is the, I'm sorry, orbital, this is the orbital for phosphorus. But as soon as you move to sulfur, what happens? Sulfur has spin pair repulsion. The first electron gets accommodated either in this or this or this, because of which there is some spin pair repulsion. Makes it easier for the electron to get removed, and therefore ionization energy decreases a little bit and then again goes on increasing. That is the graph. Oxides of period 3, from left to right, you start with basic, you see amphoteric and then acidic. Ionic bonding, then we have aluminium AlCl6, right? And then there is covalent, from giant structure to molecular structure. Chlorides, we have Al2Cl6, right? There is a covalent nature to it, right? There is coordinate bonding happening. That is an important mention. Look at the graph or look at the bonding in textbook, sorry, not graph. Then SiCl4, this is a characteristic equation for SiCl4 and PCl5. They'll ask us to identify which metal chloride it is or which metal it is, basically from these things. So if I take SiCl4 and mix it in water, it produces a precipitate and fumes. Precipitate is SiO2, fumes is of HCl. But if I add PCl5 to water, it will produce only fumes, because it produces H3PO4 plus HCl. Both of them are acidic, both of them which forms fume, right? Mix any other argon, it does not have chloride. Sodium, magnesium, and I think aluminium chloride will dissolve because they are ionic as well, right? So that is that. Then in group 2, see, simple things you have to remember in group 2, that the reactivity in group 2 as you go down the group increases because ionization energy decreases. It becomes easier to remove that electron and therefore it is more reactive. Solubility of sulfates decrease as you go down the group. Solubility of hydroxides increase. Solubility of nitrates, sorry, stability, thermal stability of nitrates and carbonates increase as you go down the group. Okay, reasons for these are not important. Basically they are saying that barium sulfate is less soluble compared to calcium sulfate, and this is less soluble compared to magnesium, no, sorry, solubility is decreasing. So magnesium sulfate is more soluble than calcium sulfate, more soluble than barium sulfate. I think I was saying the same thing. Anyway, this is that. Solubility of hydroxide increases. So barium hydroxide is most soluble in case of these three, right? Barium carbonate requires most energy to decompose. Barium nitrate requires most energy of these three to decompose. Then we have group 17. The oxidizing ability of the element increases as you go down the group. Now why does oxidizing ability increase? Because the number of electron increases, right? There are equations of H2SO4 with Hi, HCl and HF, right? HF, I don't think there are in the textbook, but these are the reactions shown. I would highly recommend you go through these from the textbook. The reactivity decreases, thermal stability of hydrogen iodide increases. So it is hydrogen halide decreases. So it is easier to decompose hydrogen iodide by heating compared to hydrogen fluoride. Okay. Then there is disproportionation reaction of chlorine. Remember it. Okay, there are just two reactions. Remember both of them. Chlorination of water. What is HClO? How does it occur? Why does it kill bacteria? That is given in the textbook. And HX with H2SO4. This is what I explained. So these three things, look at your textbook, look at whatever source you want, and learn these equations by heart. Okay, they are just textbook equations. I have not written them down here as it is. Then we have last topic, nitrogen. NO2 acts as a catalyst in forming acid rain. What happens is NO2 reacts with SO2 to produce NO and SO3. This SO3 can then combine with water to form H2SO4, which is acid rain. But this NO, it can go back and combine with half O2 or O2 to produce NO2 again. This NO2 will go back here and this cycle will keep on happening. So NO2 is acting as a catalyst. It is regenerated at the end, right? It can produce more and more acid rain, right? This is a secondary pollutant. It is not directly made by human activities, but nitrogen dioxide made by human activities makes other pollutants. Nitrogen itself is unreactive due to N triple bond N, and NH3 is basic in nature. Nitrogen dioxide also produces PANs and volatile organic compounds, right? So this is basic revision of your inorganic and physical chemistry, right? We will now first do some questions and then we will start with organic and then the questions for organic. Let's get started. Okay, so let's get some questions over here. Let's quickly. Okay, well, I think this is organic. Yes. Okay, I'll have the questions over on this side and we'll try to solve them on the other side. First question reads, identify the single reagent that can be used to distinguish separate samples of dilute MnO twice and dilute Bn, so magnesium nitrate and barium nitrate. What property can we use? If I want to use a single reagent, the property I can use is solubility of sulfates. What happens to solubility of sulfates? Magnesium was more soluble than barium. So if I use H2SO4, right, what will happen? Magnesium sulfate soluble, barium sulfate insoluble, right? So that is your reagent and your explanation. So that is from group 2 chapter. Then we have compound X. An anhydrous group 2 bromide is dissolved in water and titrated against aqueous silver nitrate. So group 2 bromide, shall I write it as ABr2? It reacts with AgNO3, right, to produce AgBr, right, and other compound. Now, a solution containing 0.250 gram of X requires 33.65 centimeter cube of 0.05 mole per dm cube of AgNO3 for complete reaction. See, this is why we cannot do it separately for each chapter. It uses mole, it uses solubility, and it will use the property that AgBr is a precipitate, right? Identify X, show your working. So first I'll find out how many moles of AgNO3 are used. Okay, so what do we have here? We have 33.65 multiplied by 0.0500, and this whole thing divided by 1000 because this is in centimeter cube, right? I'm using the formula concentration is equal to moles upon volume. Trying to find out moles is concentration multiplied by volume, right? So what do I find? I find that it is 1.68 into 10 to the power minus 3 moles. Now if you look at this, this is 1 is to 1. Okay, let's read the question again. The solution containing requires these many. Okay, so how many ever these moles are there? There are 2 times the moles of this thing, correct? Acha, I have to add a 2 here, right? Then this will make sense to you that this is double of that thing. Now, if this is used 1.68 into 10 to the power minus 3 moles, this should be half of it. So 1.68 divided by 2. So it should be 0.84 into 10 to the power minus 3 moles, which is 0.250 gram. Correct? Now, I can use the formula N is equal to M upon Mr. I can find Mr is equal to measured mass upon number of moles. So 0.250 divided by 0.84 into 10 to the power minus 3. So what do we have? We have 297 gram. That is the mass, the molar mass of this bromide. Bromine has a mass of 79.9, which should be Br2. So I must subtract 297 minus 160. So I get 137.2. I think this is the mass of strontium. They are asking identify X, the compound X. So my compound should be SrBr2, right? With all of this calculation. Then we have draw a curve on the axis to show Boltzmann distribution of energy of particles in a sample of gaseous krypton atoms at a given temperature. Label the curve T1 and label the axis. So what should be the curve? The curve should look something like this, right? This should be T1. This should be number of particles and this should be energy. That's your answer. On the diagram, draw second curve, show the distribution of energy of krypton atoms at a higher temperature. So at a higher temperature, it will be something like this, and this will be your T2. So that's your answer. Then what do we have? That's too much of a scroll. Okay. Draw a diagram that clearly shows all the bonds, types of bond present in Al2Cl6. This is why. Okay. So I need to show the bonds in Al2Cl6. So I'll draw 2Al bonded to chlorine on three sides. There is one more chlorine here, and this is bonded to these three chlorines. This chlorine is giving one lone pair of electron here. This chlorine is giving one lone pair of electron here. So this shows the type. This is the coordinate bond. All the others are covalent. Okay. Then we have the equilibrium constant Kp is given by following expression. Kp is equal to partial pressure of oxygen, partial pressure square of Cl2 at 1 into 10 to the power 5 Pascal, 500 Kelvin. 70% of the initial amount of chlorine has reacted. Calculate Kp and state its units. There is one mistake in this question, guys. I have not taken the equation for this question, but uh, I don't think I remember. No, I don't remember the equation for this. If I find, I will attach it at the end of the video. Okay, I'll try to find it and attach it at the end of the video. Magnesium peroxide MnO2 is made in the following reaction. Use the data given to calculate the enthalpy change of formation of MgO2. We'll here use the Hess cycle, right? I just told you that Hess cycle, it's an extension of the conservation of energy. But how to use this? So what we do, we take elements here, right? What are the elements? Elements are magnesium, hydrogen and oxygen, right? So how much hydrogen will be required? H2 and O2. Is this balanced? I think I think it is. Okay. This can form magnesium peroxide, right? And okay, let's follow the equation exactly like it is. It can form magnesium oxide and hydrogen peroxide. This can form magnesium peroxide and water, and this thing can actually go and directly form water and magnesium peroxide, right? Now let's balance this. This should be 3 by 2O2, right? This is what it should be. Now it says the formation enthalpy of magnesium oxide is minus 602. So minus 602. And formation enthalpy of hydrogen peroxide is minus 188 plus minus 188. And formation of water is minus 286. So minus 286 plus the formation enthalpy of MgO2, let it be X here. What is the enthalpy change of reaction? Minus 96 kilojoule per mole. Everything is in kilojoule per mole. So the logic for Hess law is that the energy change that is happening over this pathway, right? Very nice. The energy change happening over this pathway should be equal to the energy change happening over this pathway, because from both the pathways final product is same. So minus 602 minus 188 minus 96 should be equal to minus 286 plus x, right? 286 it is. So minus 602 minus 188 minus 96 plus 286 will give me minus 600. So the formation enthalpy of magnesium peroxide is minus 600 kilojoule per mole. Then we have draw dot and cross diagram to represent the bonding in a molecule of HOF. Show outer shell electrons only. So oxygen has 6 electrons in the outermost shell, should be the central atom. We have oxygen. Fluorine has dots, it has 7 electrons in the outermost shell, so this is those 7 electrons. Let's say hydrogen has, we will show it like this, only 1 electron in the outermost shell. Should not be asked in AS level, but here it is. HOF can be made by reaction of F2 with ice at minus 40. The reaction is similar to reaction of Cl2 with cold water. Suggest an equation for reaction of F2 with ice. Okay, so HOF can be made by reaction of F2 with ice. Ice is chemically water. It reacts. So when I react Cl2, it forms HClO. So HOF, right? It should form HOF. So, and something else. No, I don't think anything else is required. So that is how it forms. Okay, might not be balanced, but I think this is what it should form. Then we have HOF is unstable compound and decomposes to form HF and O2. HOF gives HF plus half O2. Draw fully labeled reaction pathway. Access provided, show the decomposition. So they are saying that this is an exothermic reaction. So I will write HOF here. I will write HF plus half O2 here. Dotted line. This is energy of activation. This is delta H, which is given as minus 139 kilojoule per mole. Right? This is the energy. And actually this should be time or something like that, progress of the reaction. Axes are already labeled here. Then we have next question. Substance Q is hydrocarbon. When 1 gram of Q is completely burned, 3.22 gram of carbon dioxide is produced. What could be the identity of Q? Now see, they are saying that CX plus HY, it's a hydrocarbon, reacted with oxygen, produces CO2 plus H2O. Now if I were to balance this, it should be X CO2 and Y by 2 H2O, right? If I take 1 gram of this and 3.22 gram of this is formed, then how can I differentiate between them? See, they don't say that how much oxygen is used. They're not saying that how much water is formed. Without that, it is impossible to find out if it is alkane or alkene or alkyne. We can only judge the number of carbon, that to judge, not actually find out. So look at the options: cyclohexane, cyclopentane, ethene and pentane. Now it is impossible to find out if it is pentane or cyclopentane, because as I said, we cannot find out what is the number of hydrogen. So there cannot be answer that has same hydrogen, right, or similar conclusion without the information. So B and D cannot be your answer. Okay, now The competition is between ethene and cyclohexane, because ethene is smaller and it is easier to balance. So I will say C2H4 plus O2 gives CO2 plus H2O. It should be 2, right? What is the mass of ethene? Mass of ethene is 12 to the 24, 24 plus 4, 28, 28, and this mass of carbon dioxide produced is 44 into 2, which is 88, right? Is it same as the ratio 1 is to, so this is 322, not this is 322, 3.22 upon 1. I don't think it is the same ratio, right? 88 divided by 28, sorry, 3.14, okay, which is not 3.22. So cyclohexene should be your answer, right? By elimination, we have removed all the other three options. Then we have elements X, Y, and Z are all in the first two periods of the periodic table. Their Pauling electronegativity values En are shown, just an arbitrary number showing Z is the most electronegative basically. Substances exist with formula XZ, YZ, and Z2. So Z is probably in group 7 diatomic molecule. Which row puts these substances in order of increasing melting point? So diatomic gas molecule should have the least melting point. So Z2 should have the lowest melting point. So only C and D can be your answer. Now if X has lower electronegativity than Y, then X is more towards the left hand side than Y. If it is more towards the left hand side, then it can form stronger ionic bonds compared to Y, which is why that XZ should have a higher boiling point compared to YZ. So your option is YZ and XZ. So answer is C. Then we have the next question. Equation for reaction 1 is shown. Reaction 1 is oxidation of glucose to produce carbon dioxide and ethanol. Now, what do we see here? That they have given the combustion enthalpy of both glucose and ethanol. Now they are asking us to find out the enthalpy change for reaction 1. So basically C6H12O6 combusts to form 6CO2 plus 6H2O, right? They are saying that this is A. Then C2H5OH can also combust to form, it cannot combust to form this, right? It will form something else, C2H5OH. So you have 2CO2 plus 3H2O, right? If it is given enough oxygen. They are saying that if this is A and this is B, then if I want to form two of this thing and two CO2, right, then what will be the enthalpy if they have the same product? Now because 2 moles of this thing are forming, right, so 2 here, the equation will become 4CO2 plus we had 3 to the 6H2O. So 4 plus 2 is again 6CO2, right? This is 4, sorry, this is 2B. The enthalpy to combust this is 2B and the enthalpy directly here is A. So how much is wasted in giving this 2CO2? That should be A minus 2B. Here energy is given out more. How much more? 2CO2 worth more. So A is the energy given out when glucose is combusted, but 2B is given out when 2 moles of ethanol is combusted, and the difference between that two is the reaction enthalpy of this reaction. Then we have next question. Two half equations are shown. The equation for reaction between magnet and it is given, which statements are correct? U is equal to X is equal to Z, manganese is reduced, sulfur is oxidized. We'll check with that. Let's first look at options. So we have 1 2 3, 1 2, 1 3 and 2 3. So if we check first option and if we find that it is incorrect, D is the answer directly. So first let's check for that only. So you have MnO4 minus plus H2O plus SO3 2 minus gives MnO2 plus SO4 2 minus plus OH minus, right? Right now we'll not do anything to OH minus and H2O. First, let's find out what is the oxidation state change in manganese. So here it is plus 7. How is it plus 7? Let's say manganese has an oxidation state of X plus minus 2 into 4 is equal to minus 1. So X minus 8 is equal to minus 1 and X is equal to plus 7. Same way, here it is plus 4. Oxygen is minus 2, minus 2 into 2 is plus 4. So it goes from plus 7 to plus 4, oxidation state change of 3 states. Here, sulfur has an oxidation state of, let's find out. So Y plus minus 2 into 3 is equal to minus 2. So Y should be equal to 3 to the 6, 6 and so Y should be equal to 4 here. And if one oxygen is added, I think Y should be equal to directly 6 here. So it goes from 4 to 6. Now, what can we write here? So ideally, we should write here, sorry, not 7. We should be writing here, the oxidation state change here is 2. Oxidation state change here is 3. Multiply 3 and 3 over here, 2 and 2 over here, right? Then how to balance this further? Check for charges. 2 ones are 2, 2 plus 6 is 8 negative charges, and you have 3 twos are 6, and to make it equal here I must add a 2 here, right? 3 twos are 6, 7 and 8 negative charges on both sides. Manganese on both sides 2, oxygen 4 twos are 8 plus 1 9, 9 plus 9 18, 4, 4 plus 12, 16, 17 and 18. Hydrogen is 2 over here, 2 over here. The equation is balanced, right? Nothing for H2. Okay. U is this, X is this, and Z is this. Yes, they are equal. So first statement is correct. Manganese is reduced to oxidation state plus 4. That is correct. Sulfur is oxidized from plus 4 to plus 6. That is also correct. Increase in oxidation state is oxidation. So first, second and third, all the three statements are correct and your answer is A. Hydrogen and iodine react to form hydrogen iodide in an exothermic reaction. The equation is shown. 1 meter cube of reaction vessel contains H2, I2 and HI gases at equilibrium. Temperature is changed such that total pressure in 1 meter cube vessel doubles. So if pressure doubles, what will happen? The equilibrium will shift towards left or right. No, it will not change. What is the effect on the value of Kp and the position of equilibrium? Because the position of equilibrium does not change, moles on both the sides are equal. Because the position of equilibrium does not change on changing pressure, the value of Kp also does not change. So option D. Then we have VO2Cl reacts with NaI under acidic conditions. The oxidation state of Cl is -1 in VOCl and VOCl2. So the oxidation state of chlorine is not changing. Which row about this reaction is correct? What is happening to vanadium? Let's check. So it goes from VO2Cl to VOCl2, right? Here, if this is X, this is -4 and this is -1 should be equal to 0. So X should be equal to 5 here, and X -2 should be equal to 0. So X is equal to 4 here. So if oxidation number increases, it is getting oxidized. If it reduces, it is getting reduced. So vanadium is getting reduced, right? Again it is forming VOSO4. Again same thing is happening. So vanadium is getting reduced. what is happening to iodine? Okay, here it is I minus, then it changes to I2. So it goes from -1 to 0. This is oxidation. The oxidation state moves rightward. So it is oxidation. So vanadium is reduced, iodine is oxidized, which is your option C. Right? Then we have dibromopentenes can undergo double elimination reaction to produce hydrocarbons. Which isomer? Okay, we'll look at this or these type of questions when we do organic. Structure represent three compounds, each with 4 carbon atoms per molecule. Which row is correct? Lowest to highest boiling point. See, here it has ions, right? So this should have highest intermolecular forces due to charges. So Z should have the highest boiling point. So either A or B, right? Then we have, because of OH, hydrogen bond forms in X. So therefore X should have the second highest boiling point and Y should have the lowest. So lowest Y, and that is the only option available. Lowest Y, then X, and then the highest boiling point. What is the environmental consequence of uncontrolled use of nitrogen fertilizers? They will wash away to the nearby lakes or rivers and then cause algal bloom, and which will cause acid rain. No. Low oxygen level in streams? Yes. Algae will take up all the oxygen and there will be lesser oxygen level in streams. Then we have compound X is an organic compound that contains 30.6% carbon, 3.8% hydrogen, and 20.4% oxygen, and 45.2% chlorine by mass. Okay, so let's write that down. So you have carbon, hydrogen, oxygen, and chlorine. So you have 30.6 divided by 12, its molar ratio. 3.8 divided by 1, I have 20.4 divided by 16, and 45.2 divided by 35.5. Let's quickly find out what happens here. So I have 30.6 divided by 12, it is 2.55. This will be 3.8. I have 20.4 divided by 16, it is 1.275. 45.2 divided by 35.5, I have 1.2732. This being the smallest, I'll just round it off to 2 decimal places, right? So this being the smallest, everything will be divided by 1.27. So 2.55 divided by 1.27 will give me 2.00. 3.8 divided by 1.27 will give me 2.99, rounded off to 3, rounded off to 2 right now. If everything else in ratio, yes, it will be 1 and 1. So what is my empirical formula? C2H3O1Cl, or rather I would write C2H3OCl. Okay, that is my answer. Then we have, in which structure are 3 carbon atoms bonded together, are 3 atoms, not carbon atoms, bonded together in a straight line? Whenever these type of questions are there, try to first find out if there are answers other than hydrocarbons, because they are likely to be correct. Silicon tetrachloride, right? Silicon tetrachloride, no, the bond angle is not 90. SF6, right? 90-degree upwards, 90-degree downwards. So I think SF6, option D is your correct answer. Again, you have to remember this from your textbook. Ethanoic acid is mixed with ethanol. Ethanol is contaminated with a small amount of methanol. Following equilibria are established. What happens? Kc1 and Kc2 are established such that ethanoic acid reacts with ethanol to form ethyl ethanoate, and ethanoic acid reacts with methanol to form methyl ethanoate. Right? Which statements about the equilibrium mixture is correct? Only ethyl ethanoate will be formed. because there is much more ethanol present than methanol. No, both of those are present. In this mixture, K1 upon K2 is equal to product or ethyl ethanoate upon methyl ethanoate. I don't think that is, let's check. Okay, so what do we have? We have K1 is equal to, acha, but their denominators are not common, they'll not get cancelled out. See here, the second reactant is different in both of them, they'll not get cancelled out, so this cannot be an equation. Adding water to the mixture will alter the mole ratio of the two esters. They are already dilute, right? It cannot happen. Water cannot alter the rate of reaction or disturb the concentration. Okay. Adding methyl ethanoate to the mixture will increase, I don't know what, but adding methyl ethanoate, adding somewhere of these two or either of these two, that will change the equilibrium. Adding methyl ethanoate to the mixture will decrease the number of moles of ethyl ethanoate. How will that happen? If I add methyl ethanoate, the equilibrium shifts towards this side. So when this increases, okay, then when this increases, the first equilibrium goes towards the right hand side. We just studied that the concentration or the amount, if I change, the Kc will remain same and the concentration of the reactants or the constituents of the reaction will change, right? So that is going to happen, and that is why option D is the correct answer. Which graph correctly shows relative electronegativity plotted against relative atomic radius for elements sodium, magnesium, aluminium and silicon? Sodium has the lowest electronegativity, so C cannot be your option. Then we have silicon has the highest electronegativity, so B cannot be your option. Then what do we have? What do we know about these four? Atomic radius should be in a series because all of them are their consecutive elements. So sodium, magnesium, aluminium and silicon makes more sense compared to sodium, magnesium, aluminium and silicon over here, right? So A should be your answer. Then we have X, Y and Z are three elements in group 17. X2 has weaker covalent bonds than Y2. X2 has stronger instantaneous dipole induced dipole forces between its molecule than Z2. So this is somewhat, if I write them according to their period, right, in the same group, I think this should be, because X2 has weaker bonds, so X2 is above this, and it has a stronger dipole induced dipole than Z2, dipole induced dipole. Okay, so Z2 should be compared with X2. Iodine has stronger dipole induced dipole compared to bromine, right? So it should be over here, and weaker, so this should be over here. What could be X, Y and Z? So chlorine, bromine and iodine, this is what it should be like. Weaker covalent bonds, yes. Stronger instantaneous dipole than Z2, yes. So X is Br2, okay, option A. But let's check. Y is Cl, okay, something is wrong. And Z is, just a second guys, let's redo this, not finding an option. X2 has weaker covalent bonds than Y2. It is easier to react with iodine compared to fluorine, okay. Then X2 has stronger instantaneous dipole, induced instantaneous dipole. So I am sure that X2 has weaker instantaneous dipole. So X2 and Y2 are at least like this. And Y2 is a stronger oxidizing agent than Z2. Iodine is a stronger oxidizing agent than, okay, so Z2. So X should be iodine in this case. Y should be just above iodine, bromine, and Z should be just above bromine. Chlorine, does this find something? Chlorine, bromine, and iodine. So somehow I am finding a C rule here, right? I hope all of you know C rule. If you don't find any answer, tick C. Most of the time it's correct. And yes, this is the correct answer now. Okay. Chlorine is bubbled through a cylinder containing aqueous sodium iodide and an immiscible layer of hexane. Okay, as the bubble pass through the cylinder, what is observed in lower and upper layer? Because it is aqueous sodium iodide and chlorine gas is bubbled, iodine will be displaced, and with hexane it will give a color change, right? All three of them have different color with hexane. So lower aqueous layer, colorless solution, becomes brown. Okay, upper hexane layer, colorless liquid, becomes colored. Okay, so A is your answer. There are two naturally occurring isotopes of bromine. One isotope has 44 neutrons, the other isotope has 46 neutrons. Ignoring fragments, how many peaks are there in mass spectrum of tribromomethane? So we have 12C, 1H, Br3. So ignoring, due to this, I have 3 bromine, right? So 44, the arrangement possible is 44, 46 and 46. I have 44, 44 and 46, 44, 44 and 44, and finally 46, 46 and 46. So 1, 2, 3 and 4. 4 peaks due to this bromine, tribromomethane. So answer is C. Then we have equation shows H2 and I2 react to form equilibrium mixture. Okay, the reaction is exothermic. Mixture containing equal amount of H2 and I2 is made at temperature T1 and the composition of mixture is monitored. A graph of result is shown. Experiment is repeated at lower temperature T2. Which new graph would be obtained? Now, if it is at a lower temperature and the reaction is exothermic, right, the equilibrium will shift towards right. More of iodine would decompose. So that is the first thing. So it will go below 0.23. It goes below 0.23 only in one graph, and that is B. But if you see, the time has extended. Why? Because, has it extended actually? Yes, it has. Which new graph? Because if it is at lower temperature, the rate of reaction also decreases, and that is why B is your answer. With which we come to the end of inorganic or physical chemistry. Let's quickly get started with organic chemistry. Okay, so we shall start with the first organic PDF. Yes, let's close this for now. So we have the first topic of organic chemistry, and that is introduction to organic chemistry, right? uh, I've made some quick notes. We'll quickly go through it. Will not try to, I'll try to make the video as short as possible. So we have types of formula. The first formula is skeletal formula. Most questions do demand that you know the skeletal formula. If you know the skeletal formula, your answers will become really easy, right? This is a skeletal formula and it is a 3D formula. It shows the angle of bonds, right? That the hydrogen and CH3 are coming out, this hydrogen, that CH3 is going behind, right? So these are the different types of formula. But there is something known as hybridization, right? How does bond form? I'm not going to go into every detail, but we'll try to keep it with important topics. So hybridization and bonding, as I was telling you in the chemical bonding chapter, that I'll teach you hybridization and bonding. So what happens with carbon is two of its orbital are s and one is p, right? The s1 are spherical in shape, the p is dumbbell in shape. Now see, what happens is when SS, SP and PP can combine head on, it forms a sigma bond. But when they cannot combine head on, they combine sideways, right? This is known as a pi bond. Now, why is pi bond required and how does it happen? Basically, imagine that carbon has uh, 3 bonds, right? It wants to form 4 bonds basically, each with hydrogen. Let's imagine that there is methane forming, right? Now it wants to keep all the hydrogen at the same energy level, so it should keep all the hydrogen at equal distance, at equal energy from it, correct? So what it will do, it will try to have same kind of bonding with all of them. Now see, three there are 3p orbitals, correct? And there is one s orbital, right? See, look at this here. So you have s, this is one s orbital, and there are 3p orbital, but the accommodation is something like this right now. If carbon wants to keep all the hydrogen at same level, what it will do, it will ask 3p orbitals and one s orbital to participate in a hybrid orbital, such that all four of them are at the same energy level, filling one electron each. What this will help in, it will help in accommodating the hydrogen, right? This type of hybridization is known as sp3 hybridization. There are 3p orbitals, one s orbital. If 2s orbital and 2p orbital and 1s orbital come together, it is known as sp2 hybridization. Now where does sp2 or sp3 hybridization come in picture? Now if carbon wants to form another bond with the carbon, right? So let's imagine that it is ethane. Okay, carbon has formed bond like this with all hydrogen, 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 hydrogen. Now, if due to some reason, right, or if naturally there were no hydrogen here, the carbon would like to still form bonds and another bond with this carbon. Now, what happens here is that there is already a bond sharing on all sides, right? And these hybrids are spherical in nature, so it is already sharing electrons over here. Now if it wants another bond, it will have to somehow form over here, which is a little difficult because again electrons will repel each other. So what will carbon do? Carbon will take out one orbital from the hybrid and form this sideways overlap. Okay, so let's say this is the hybrid sp2 orbital. It is bonded to hydrogen, 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 and another carbon, right? Shown 4 hydrogen bond. Let's say here there is another carbon. Now if it wants to form another bond with the carbon, so what it will do, it will release this from the hybrid and overlap will take place over here, which is what a pi bond is, right? Which is what a pi bond is. So if there are only single bonds, the hybrid is sp3. If there are double bonds, the hybrid is sp2. And if there are triple bonds, hybrid is sp3. This is true for any carbon compound and for that matter nitrogen as well. The N2 molecule is sp hybridized because it has triple bond. Then there is general naming. I've just kept it here. I'm going to share this whole thing, whatever I've written, as a PDF, right? So you can download it and you can write your own notes into that. Now we have isomerism. Isomerism comes from the naming. When two compounds have same structural formula but different molecular formula, they are known as isomers. There are different types of isomers. The first is structural isomer. So in structural isomer, the first one is positional isomer. So if you notice, this bromine is on first carbon, this bromine is on second carbon, this bromine is on first and this is on third. So this is C3H123456 H6Br2. This is also the same thing, but their molecular formula, their structural formula, I mean, are different and they will have different chemical properties because of this. Then functional group isomerism, again same structural sorry, same molecular formula but different structural formula. Right here this is OH and here oxygen is between two carbon. Then chain isomerism. So what happens is the chain length, here the chain length is of 4 carbon, here the chain length is of only 3 carbon, right? So chain length isomerism. Then we have cis trans isomerism. So because this 1p overlap takes place, 1p overlap takes place. So what happens is, so let's say this is carbon, right? It has already overlapped like this. Now it wants to form another bond, it must overlap like this. So until unless it was overlapping like this, the two carbon could rotate. They had free rotation. But as soon as this overlap takes place, they cannot rotate individually anymore. So chemical properties of a compound that looks something like this, right? Hydrogen and having CH3 on the same side, these are two different compounds having different chemical properties, because this cannot rotate anymore to bring CH3 in front of the other CH3, right? It will always stay at the cross, which is why this is known as trans and cis isomer, right? Cis trans isomerism, also known as geometric isomerism. Then there is optical isomerism. Now see, your left hand and your right hand look exactly the same, right? But can I superimpose my left hand over my right hand? No, they will look different no matter what direction I rotate. But as soon as I look at my left hand in a mirror or my right hand in a mirror, it looks like the other hand. So until unless there is a mirror plane, the two compounds cannot superimpose over each other. This requires that the four group of atoms or atoms connected to the central carbon are different, and this carbon is known as chiral carbon. Okay. Then we have types of organic reaction. There are various types of organic reaction. We'll see throughout this revision. Addition reaction, only single product forms. That is the identity. Elimination reaction, two or more products form. Condensation reaction, it's a two-step reaction where addition takes place and then elimination of a smaller molecule takes place. Oxidation reaction, using KMnO4 or K2Cr2O7, aqueous and acidified, they will change the oxidation number of some of the reactants. That is why it is known as oxidation reaction. Reduction reaction, again, you add hydrogen, so LiAlH4 or NaBH4, in which LiAlH4 is a stronger reducing agent, right? Now what do we have? We have substitution reaction. Types of substitution reaction: free radical substitution. Where does this free radical come from? We'll see in some time. But if there is CH4 and I add chlorine in UV light, chlorine will replace one hydrogen and form chloromethane, right? CH3Cl and HCl. Hydrolysis, just add water. Okay, this is because it uses hydroxide, it is base hydrolysis. This uses water and H plus ions. This is known as acid hydrolysis. The products of base and acid hydrolysis are different, just remember that. Okay, here it's same, exactly the same, but the other products are different. Okay, then what do we have? Right, we have the types of hydrocarbon. Okay, the types of carbocation. There are three basic types of carbocation. One is known as primary, second is tertiary, second is secondary, and the third one is tertiary carbocation. What is the difference and how do they matter? Their reaction mechanism will be different. We will see nucleophilic substitution, the SN1 and SN2 type of reaction. But basically what is happening, primary is when carbon is surrounded by just one carbon, secondary when surrounded by two carbon, tertiary when surrounded by three carbon. What happens is the central carbon that we are talking about right now, when it wants to become a carbocation, the carbon around it will provide positive inductive effect, meaning it will let it become a positively charged ion more easily the more the number of carbon around it, the easier for it to form the positive ion, which is stable. Okay, so tertiary is more stable. The tertiary carbocation is more stable compared to secondary, and secondary is more compared to primary, right? How are free radicals made? Right, we just discussed in the last slide. Homolytic fission. Homolytic meaning both of them will take away same number of electrons. So Br and Br. Heterolytic fission, when there is a difference in electronegativity, one of the atom takes away both the bonded pair of electrons. So bromine has a negative charge. It has a bonded pair of electron with it. We will now show it as it has both the electrons, has two dots, and H plus. So H plus becomes electrophile, Br minus becomes nucleophile. Nucleophile because it is searching for positive charge, electrophile because it is searching for a negative charge, right? So that is introduction to organic chemistry. Let's see what else do we have. Then we start with alkanes, right? So we have alkanes. Alkanes are saturated hydrocarbons. Reaction of alkane, first reaction is combustion. Any alkane, if it is in supply of proper oxygen, it will always form carbon dioxide and water. If there is insufficient supply of oxygen, it will form carbon monoxide and water, right? Engines, if they are not fine tuned, can also produce carbon monoxide, right, with carbon dioxide. And because there is high pressure and temperature, it can also produce nitrogen monoxide or oxides of nitrogen, right? So NO can be put into catalytic converter with carbon monoxide to produce nitrogen dioxide. But this nitrogen dioxide, as we've already seen, can act as a catalyst, right? So that is there. Then we have substitution reaction of alkanes. What happens in substitution reaction of alkanes? And here we see mechanism of organic reactions. The first mechanism, right? So we have, what is this? Ethene plus chlorine gives chloroethene and HCl. This is one step, right? But how does it happen? So for any reaction to start, there must be a free radical made. This free radical making is initiation step. How to identify initiation step? On the left hand side, no radicals. On right hand side, at least one radical, right? Here UV light acts as the energy provider for this reaction to take place, and this is homolytic fission. Both chlorine take away their own electron that was shared. Then what can happen? This chlorine can directly go to C2H6 and it can take away one of the hydrogen to form HCl. So now you have one radical, right, which is ethyl. C2H5 group is left. Now this C2H5 group has an electron that it wants to share with someone. So this becomes a radical, right? This other chlorine can combine with the C2H5 that it itself produced and form C2H5Cl. Now, if you look at this last step, right, what happens? On left hand side I have two radicals, but on right hand side, yes, on left hand side there are two radicals, on right hand side there are no radicals, which means that this is a termination step. Now here this becomes my final product. So wherever there are no radicals on your right hand side, the product side, it is a termination step. But this C2H5 can then react with another C2H5, right? It's shown here, which is also a termination step, right? Another C2H5 may be simultaneously created and both the C2H5 are searching for something to share their electrons. Then it can result in C4H10. Then what else can happen? This C2H5Cl so formed can again react with more chlorine to form more C2H4Cl, because chlorine will take away one more hydrogen. This can keep on happening until I have C2Cl6, right? If there is enough chlorine, this can keep on happening again and again and again. But again, this C2H4Cl can combine with Cl to form C2H4Cl2. Again, this is a termination step. So sometimes you are asked about finding what is the termination step or the initiation step or the propagation step of a reaction. This is how you should identify that. Then we have alkenes. Alkenes are unsaturated hydrocarbons. They have general formula CnH2n. They are produced by cracking using aluminium oxide and heat cracking of long chain alkanes. Then we have elimination of hydrogen halide. If you eliminate one hydrogen and one halide from a hydrogen halide, then you can form alkene, right? You can take chloroethane and remove chlorine and hydrogen from neighboring carbon. It's ethane, so they are both in neighboring carbon, and you can form ethene, right? Using ethanolic sodium hydroxide. Then we have dehydration of alcohol. If you dehydrate alcohol, meaning remove OH and H from neighboring carbon, then you can form ethene. You can use Al2O3 or H2SO4 for this reaction. Okay, nothing else here. Then we have addition reaction in alkenes. In alkenes, because they can be produced by reduction or dehydration reactions, we can again oxidize or hydrolyze these to produce new compounds, right? If you add Y and Z, right? If you add Y and Z, example, if it is water, right? So one is H and other is OH. If it is HBr, then the compound formed will be like OH and H. This compound is an alcohol. If instead of OH and H you had H and Br, then this is halogenoalkane, right? Then XX, what are these? These are halogens. So you can form dibromo, dichloro, right? You can also add hydrogen. This is known as hydrogenation reaction. Now let's see how to do all of these reactions. So if I want to add hydrogen, I have to use platinum and nickel as catalyst. This is known as hydrogenation reaction. If I want hydrogen halide, I just have to use concentrated HX, right? Product will depend on the carbocation available. So if there is a secondary carbocation, product will be according to that. If there is a tertiary carbocation, product will be according to that. Then how to add steam? Concentrated H3PO4 and halogen characteristic reaction, right? What does characteristic reaction mean? If I want to find out that if my hydrocarbon is unsaturated or not, I just pass it through and I'll pass it through halogen. If the halogen decolorizes, my compound is unsaturated. So it's an identity reaction, it's a characteristic reaction. Then mechanism of electrophilic reaction. So what do I mean by availability of the carbocation? Right? We will see it later on. I think this is a different thing. Well, let's check it out quickly. So what will happen if this bromine is coming near? Because of high electron density over here, this will become positively and negatively, slightly negative charge. As soon as that happens, these electrons are attracted to this bromine and these electrons leave this bromine and go here. So there is Br minus available, but this directly bonds to Br. Now because both the carbon have one carbon around them, both of them are primary. Instead of this, if there was a carbon available here, then this carbon will first bond, this carbon will first bond to bromine. This carbon has a stabler carbocation. So this will be positively charged, and this Br minus, it's a nucleophile. It wants a positive charge. So it gets attracted here and forms this bond. So this is how electrophilic addition reaction in alkenes can take place. Then we have oxidation of alkenes. Now oxidation of alkene will depend on what is on either side of the carbon that we are oxidizing. Okay, so let's look at this carbon. We have, if hydrogen on both sides, then oxidation will form carbon dioxide and water, right? If there is one carbon group and one side there is hydrogen, first it will form aldehyde. If I don't distill off this aldehyde, it will immediately form acid. Then if on both of the sides there are carbon group, then it can maximum form ketone. It cannot be oxidized beyond being a ketone. right? So that is the part of alkenes. Then let's go to the next slide quickly. We have, yes, halogenoalkenes. This is going to be a longer chapter with a lot of learning, right? Because this has a lot of mechanisms in it. Halogens are generally reactive. They help organic compounds to become reactive. What is the general formula? Cn H2n plus 1 X. They are not found naturally but helpful in reactions, so they are prepared. Methods of preparation: free radical substitution in alkenes, we have already understood them. Electrophilic addition in alkenes, we just saw that. Addition, substitution in alcohol. Substitution meaning replacing the OH group in alcohol with HX or KX with H2SO4 or H3PO4. What is X? X is halogen. Sorry. So we have CH3CH2OH, ethanol. With HCl, it will produce CH3CH2Cl and water, right? If I want to produce it with PCl5, I take alcohol, PCl5. If I take PCl5, I have to use heat. The product is H3PO3. If I use PCl3, I have to take heat. If I use PCl5, it will happen at room temperature, but the product is HCl. So fumes are produced and POCl3 is produced with that. If I use SOCl2, again at room temperature, this will happen. Here HCl and SO2 are given out. So here, if you look at this product is constant, right? Its ratio obviously changes with the reagent, but the product remains constant. Alcohols can be used to produce halogenoalkanes, and we will see that halogenoalkanes are also used to produce alcohol. Then strength of bond and bond length. In halogenoalkanes, the bond length of HF is shortest and therefore it is the strongest bond. HCl is weaker, HBr is weaker, and HI is weakest. I think I've already explained in the non-organic part that this is easiest to break, right? It takes least heat energy to break. Then nucleophilic substitution reaction. I can substitute the halogenoalkane, right? The halogen in halogenoalkane with other things, right? If I use alkaline sodium hydroxide, it will form alcohol and sodium bromide. If I use Cn minus in ethanol and KCN, right? Not HCN, not HCN plus NaCN, only KCN is used, then I can actually extend the chain length, right? So I started with bromoethane and I ended with ethane, propane nitrile, right? And KBr. We'll see the mechanism in detail. With NH3 in ethanol, it produces CH3, CH2, NH2 with HBr. Then mechanism of nucleophilic substitution. Now first we will understand positive inductive effect, right? So if it is primary, it has the least positive inductive effect, secondary a little bit greater, and if it is tertiary, then the positive inductive effect is the largest in this case, right? We will see how this helps in the, or how this interferes in the mechanism of electrophilic substitution. Let's see. So if I see, if I have primary carbocation like this, what is this? This is bromoethane. And if I have tertiary carbocation, it is something like this. Okay, C is bonded to Br, and there is CH3 on all the three sides. Okay, now what will happen? Acha, there is already a diagram. What will happen? So I have NaOH. Oh, it is not ethanolic. Here we just saw that NaOH is aqueous. Okay, this aqueous NaOH, what happens is, because bromine is very electronegative, it wants this electron, it takes away this electron, and OH minus, it itself is negatively charged, will come to this positively charged carbon. But because carbon is not getting a lot of inductive effect, it will form an intermediary where it is bonded to both of them, which is why it is known as nucleophilic substitution of order 2. The rate of reaction will depend on concentration of OH minus and the concentration of halogenoalkane. Here, what happens is that there is a lot of positive inductive effect. So this carbon can afford to leave that electron and form an intermediate where it is positively charged, right? Here, OH minus is readily accepted. There is no intermediate with both of them because there is no intermediate, or it is a one-step reaction, right? It is known as SN1, nucleophilic substitution of order 1, right? Sodium is already present, right? Sodium Na plus, because it gave off Br minus, so sorry, OH minus. So this Br minus that is given off from this reaction gets attracted to sodium and forms NaBr, right? Like so. Then, so halogenoalkane plus sodium hydroxide, I have still written ethanolic, please ignore this. It will give alcohol plus sodium halide. If it is tertiary, it will form SN1, or it will follow SN1 reaction. If it is primary, it follows SN2 reaction, right? If it is secondary, it can follow either of them. Elimination reaction, ethanolic sodium hydroxide plus heat, halogenoalkane, ethanolic sodium hydroxide will directly form alkene, sodium halide and water, right? If it is elimination, use ethanol. Okay, remember this. If it is elimination, use ethanol. And that is all about halogenoalkane. Okay, where do we reach now? We've done halogenoalkane, so we'll go to alcohol, esters and carboxylic acid. So what is an alcohol? Alcohol is a compound which has a general formula of CnH2n plus 1 OH. OH is known as its functional group. Okay, this is again a little bit of correction. These are less acidic than water. Alcohol is less acidic than water. It does not leave the H plus ion as easily as water does. Okay, so there can be three possibilities of alcohol. This is primary alcohol connected to just one carbon, or OH group connected to the carbon that itself is connected to just one carbon. This is secondary alcohol, right, where this carbon is connected to two other carbon. And this is tertiary alcohol, where this carbon is connected to three other carbon. This will change its reactivity, and that is why we study that. Preparing alcohol, just like we prepared everything else, we will also study preparing of alcohol. Alkene plus water in presence of acid, H3PO4 or H2SO4 gives alcohol. Alkene in cold dilute KMNO4 will produce diol, right? We will also see this as a characteristic reaction. Achha, we should have seen this in oxidation of alkene, but because this is also preparation of diol, I've kept it here, right? This, if you add it to cold dilute KMNO4, it will form this diol. Then nucleophilic hydrolysis of halogenoalkane, right? If halogenoalkanes can be produced from alcohols, alcohols can be produced from halogenoalkanes, right? The same reactions, those PO4 and all of those reactions can be reversed. Reduction of aldehyde can also produce alcohol. CH3, I've written COH because oxygen is bonded to both hydrogen and carbon. It can be reduced to form alcohol, right? Ketone can be reduced to form secondary alcohol, and acids can be reduced to form primary alcohol. But this requires LiAlH4 in presence of dry ether because it is strong enough to do this, right? NaBH4 is not strong enough to reduce acid directly to alcohol. Okay, remember this. Or you can use hydrogen in platinum or nickel catalyst. Then you have hydrolysis of esters. Hydrolysis of esters can also form alcohol. Base hydrolysis, which is faster. Okay, I have sorry about that, guys. This is acid hydrolysis and this is base hydrolysis, right? Because I am using sodium here, right? And this is acid hydrolysis because I've used H plus here. So acid hydrolysis is slower, base hydrolysis is faster because sodium ion readily forms. Okay, so here what will happen, I will see that this ester, when I add water in presence of acid or when acid is dilute, it hydrolyzes this ester to form acid and alcohol, right? Same thing happens with sodium hydroxide as well, but instead of acid it forms a basic salt. What this salt is? Sodium ethanoate, right? The alcohol forming still remains as it is. Reactions of alcohol is equal to preparation of halogenoalkane from alcohol, right? So again, all of these reactions that we studied back in halogenoalkanes. Reactions of alcohol with sodium metal, it will react with sodium to produce sodium ethanoate, sodium oxyethanoate, and give out hydrogen gas. Esterification reaction, alcohol can react with acid in presence of concentrated acid, right? This is a mineral acid and this is an organic acid. It can react with an organic acid in presence of concentrated mineral acid to produce ester and water. Dehydration. So alcohols can be dehydrated to form alkenes and water, right? Oxidation of alcohol, if it is primary alcohol, it can be oxidized to aldehyde. Aldehyde can be oxidized to carboxylic acid. If it's a secondary alcohol, it can be oxidized to only ketone, and if it is tertiary, it cannot be oxidized to anything. And this can be used to differentiate between the three alcohols. If I add KMNO4, only tertiary alcohol will not react, the other two will react. So I know which of the test tube contains tertiary alcohol basically. Carboxylic acid, how do we prepare carboxylic acid? We've already seen this. Oxidation of primary alcohols, oxidation of alkenes, oxidation of nitrile. How do we oxidize nitrile? So when I add this Cn to this, I will add H2O and I will add it with HCl. What will this do? This will make this to CH3 CH2 COOH, right? Met propanoic acid and NH4Cl will be formed with this, right? It changes the nitrile to carboxylic acid, that is oxidation. Reaction of carboxylic acid, typical acid, it reacts with bases to form salt and water, reacts with metals to form salt and hydrogen, reacts with metal oxide to again form salt and water. Reduction of acid produces alcohol, right? Because acid is always on the last carbon, so it will always produce alcohol, or it can also produce aldehyde, right? If I reduce it only to a certain degree, it will form aldehyde. So that's about alcohols, right? Esters, alcohol and carboxylic acid. Now we have, last but not the least, we have aldehydes and ketones. Now, how do we prepare them? Aldehydes are prepared by oxidation of primary alcohols. Ketones are prepared by oxidation of secondary alcohols. Tertiary cannot be oxidized. Reaction, reduction, reduction. They can be reduced to alcohols. They can be also reduced to alcohols. That is what I meant to say when I said reaction, reaction. So, nucleophilic addition with HCN in NaCN or KCN. In the previous reaction, we had used just KCN. Here, we are going to use HCN in NaCN. So, NaCN will act as a catalyst. HCN will act as a reagent, right? In the previous reaction, NaCN was acting as a reagent. Now, both produce 2-nitrile. Both of these produce 2-nitrile, right? So, let's say there is R group here, R group here. That is how it is ketone, right? Or it can be aldehyde as well. Even if there is an H group here, this will happen. So, what happens is this Cn minus tries to go near this. This takes away electron because it is electronegative, forms O minus, and Cn attaches itself to this carbon, right? This carbon now is stable, but this is negatively charged. So this tries to attract the hydrogen and the cyanide, they have a bond, but it will donate the electron to cyanide and thus forming this again, right? So basically this comes from NaCN, right? NaCN donated this. So right now Na plus is present and HCN is present, but then HCN donated this. So HCN donated the hydrogen, right? So what is present? Only Cn is present. This Cn will go and combine with sodium. Now something I want you to observe here in this mechanism, I'm sorry I did not point it out before this, that you should always draw lone pair of electron, you should always draw the negative charge. Your arrow should go from lone pair of electron to the atom, always. It should also go from bond to the atom always if it is gaining that negative charge, right? It should not be how positive charge attracts, it should be how the Cn minus or OH minus or Br minus, how they travel. So that should be your arrow. Please take care while writing your answers. And finally, what do I have? I have recreated this Cn minus ion from which I started, and therefore what will happen, this Cn will go back to the Na or K it came from, and that will act as a catalyst, right? Then what do we have? How do we test for aldehyde and ketone? If I add 2,4-DNPH, both of them will give a orange precipitate, both of them are positive, but alcohols are negative with this reaction. Okay, they give a negative test to this. Carboxylic acid, they are negative to this. So what can I distinguish? If I have 5 solutions and they have asked me identify the tertiary alcohol, identify ketone, identify aldehyde, I can do that. What I'll do, I'll first try to oxidize them. Okay, the one that does not oxidize is tertiary alcohol. The one that gives positive test for both of them is either an aldehyde or a ketone. So I'll do further testing and I'll add Tollens reagent, alkaline Tollens reagent. If it is positive, it is aldehyde. If it is negative, it is ketone, right? Silver mirror appearance is there. Then I have triiodomethane test. So this test was positive for aldehyde. This test is going to be positive for ketone, right? Positive test for ketone. So what happens is, so triiodomethane test, this is known as triiodomethane, but this is the product. Here these are the reagents that are used to test this. Here this is the end product. Okay, it is a yellow precipitate whose melting point is 109 degrees Celsius. So you can even test that if it is a triiodomethane or not. What is triiodomethane? CHI3 is known as triiodomethane. But this test can give a false positive if it is ethanol or if it is a secondary alcohol, right? Why? Because this test checks for C, sorry, it checks for this group if there is oxygen on second carbon or not. In case of ethanol, right, it will give a positive test because the first step is halogenation. It will get halogenated and then hydrolysis, it will also get hydrolyzed. Secondary alcohol will also undergo the same step, and therefore that will also give a positive test. Other than that, nothing will give a positive test. So I can even identify from the 3 alcohols I had, the 2 that did not get oxidized, one of them is going to give a positive test with this, right? It should be a secondary alcohol. So if it is on the second carbon, secondary alcohol on second carbon, then it will give a positive test. If it is on third carbon or somewhere else, it will not give this positive test. With this identification and all of this revision is over. Now, due to a little bit constraint of time, I could not do questions for organic chemistry. I'll try to post it before your exams by tonight. If time allows, if I have time after the doubt session or before the doubt session, I'm really sorry about that. But I hope you appreciate this. Give it a thumbs up and subscribe to our channel. Thank you for watching. All the best for your exams and